Imagine standing beneath a sky lit by a sun so small you could block it with your hand. Yet despite its size, that tiny star could unleash radiation storms powerful enough to erase entire atmospheres. And orbiting that star is the closest potentially habitable world ever discovered, a planet only 4.2 light-years away. Proxima Centauri b, a world humanity may one day reach. But if we ever arrive there, what would we actually find? A second Earth? A frozen wasteland? Or a planet trapped beneath eternal storms under the light of a violent red sun? Because Proxima Centauri b may be one of the most dangerous Earth-like planets we've ever discovered, and this alien world is waiting just beyond our cosmic doorstep. The story begins with a tiny star hidden deep in the southern sky, Proxima Centauri, the closest star to us after our Sun. For thousands of years, humanity had no idea this star even existed. You cannot see it with your naked eyes. It's far too dim. But in 1915, astronomers finally discovered it, a faint red dwarf quietly orbiting the larger Alpha Centauri stars in darkness. And despite being the closest star system to Earth, Proxima Centauri is incredibly alien. Its mass is only about 12% of the Sun's. Its light is dim, red, weak. If Proxima Centauri replaced our Sun, Earth would rapidly begin freezing. But around this tiny star, something extraordinary was discovered. In 2016, astronomers detected subtle movements in the star itself. Tiny wobbles, signs that something invisible was orbiting it, something with mass, something possibly Earth-sized. That planet became known as Proxima Centauri b, and suddenly, the closest star system to humanity was no longer just a star. It contains a possible world, a place, a destination. But this is where things become strange, because Proxima Centauri is not alone. It is a triple star system. Far beyond the orbit of Pluto, far beyond the frozen edge of our solar system, Proxima drifts alongside two much larger stars, Alpha Centauri A and Alpha Centauri b. Together, they form the closest star system to Earth. But the scale of this system is difficult to imagine. Alpha Centauri A is a star remarkably similar to our Sun, slightly larger and brighter. Beside it orbits Alpha Centauri b, a little smaller, a little dimmer, an orange-tinted star locked in a slow gravitational dance with its companion. The two stars circle each other endlessly over nearly 80 Earth years. If you stood on a planet near Alpha Centauri A, you would see another sun hanging in the sky, not a tiny point of light, a real star, bright enough to cast shadows at night. But then there is Proxima Centauri, tiny, cold, distant. Unlike the other two stars, Proxima lies trillions of kilometers away from them. So far away from Proxima Centauri b, Alpha Centauri A and Alpha Centauri b would appear only as brilliant stars in the darkness, bright but distant. And yet gravity still binds them together. Slowly, over hundreds of thousands of years, Proxima moves around the Alpha Centauri pair in a gigantic orbit so enormous that humanity has never witnessed a full revolution. This makes the system feel less like a normal solar system and more like three stars wandering through space together. But despite being the smallest star in the system, Proxima is the most violent of them all. While Alpha Centauri A and Alpha Centauri b are relatively stable stars, Proxima Centauri is a red dwarf, a star smaller than our Sun, cooler than our Sun, but far more dangerous. And that danger may decide whether Proxima Centauri b is truly habitable or completely dead.
Proxima Centauri b orbits unbelievably close to its star, so close that an entire year there lasts only about 11 Earth days. 11. Imagine Earth orbiting the Sun every 11 days. That sounds impossible for life. And around our Sun it would be. But Proxima Centauri is so faint that despite the close orbit, the planet may receive roughly similar amounts of energy to Earth, meaning temperatures there could potentially allow liquid water to exist. And that changed everything. Because liquid water changes a planet from interesting to potentially habitable. But there's a problem, a massive one. Proxima Centauri is not a calm star like the Sun. It's a red dwarf, and red dwarfs can be violent, extremely violent. Massive stellar flares erupt from the star, blasting space with radiation. Some flares may be hundreds of times more powerful than anything Earth experiences from the Sun. Imagine standing on the surface of Proxima b as the sky suddenly erupts with ultraviolet radiation and charged particles. If the planet lacks a strong magnetic field, those eruptions could slowly strip away its atmosphere entirely, turning the world barren, dead, sterilized. And scientists still don't know whether Proxima b survived that process. Red dwarfs are often most violent early in their lives. For millions of years, possibly billions, Proxima b may have endured relentless radiation storms, enough to boil oceans away, enough to destroy atmospheres, enough to transform a potentially habitable world into a cosmic wasteland. But maybe not. Some models suggest the planet could still retain an atmosphere, especially if it formed with massive oceans, or a thicker atmosphere than Earth. And if that atmosphere survived, something incredible may happen. The star's heat could circulate the planet, redistributing temperatures because Proxima b is likely tidally locked, one side permanently facing the star, the other is trapped in endless darkness, no sunrise, no sunset. One hemisphere may live beneath eternal daylight, while the other never sees its star at all. Imagine standing exactly between those two worlds, on the boundary, a region scientists call the Terminator Zone. One horizon glows beneath a frozen red sun, the other disappears into endless night. That narrow region may be the most habitable place on the entire planet, and the sky there would look nothing like Earth. The star would glow with a deep red hue, dimmer than our sun, but still dominating the sky. A permanent crimson twilight could illuminate the landscape. Dark oceans, frozen continents, towering clouds reflecting red light across alien skies. And somewhere above you might see another star shining in the distance, our sun, a tiny point of light in the darkness. Everything humanity has ever known is reduced to a single, distant star. But perhaps the most astonishing part of Proxima Centauri b is not the planet itself. It's the distance. 4.2 light-years. That sounds enormous, and it is. But on a galactic scale, it's unbelievably close. Practically our cosmic next-door neighbor. If humanity ever becomes an interstellar civilization, Proxima b may become our first destination, our first alien world. And scientists are already thinking about how we might reach it. One of the most ambitious concepts ever proposed is called Breakthrough Starshot, a plan to send tiny spacecraft accelerated by gigantic Earth-based lasers. These probes could potentially travel at around 20% the speed of light, fast enough to reach Proxima Centauri in roughly 20 years. 20 years. For the first time in human history, interstellar travel shifted from pure science fiction to theoretical engineering. Imagine receiving the first real images from another star system. Alien oceans, dark continents, clouds moving beneath a red sun, or perhaps nothing at all. Because there's another terrifying possibility. What if habitable planets around red dwarfs only appear habitable from far away? What if many of them are actually dead worlds stripped bare by stellar radiation? That question matters enormously, because red dwarfs are the most common stars in the galaxy. Most worlds in the Milky Way orbit stars like Proxima Centauri, meaning the future of life in the universe may depend on whether planets like Proxima b can truly survive. If humanity ever sends something to Proxima Centauri b, it will not be a spaceship in the traditional sense. It will not carry astronauts. It will not have engines as we understand them, and it will not slow down upon arrival. It will be something radically different. Breakthrough Starshot proposes a method so extreme that it bends our usual idea of space travel. Instead of building a single massive spacecraft, the idea is to build thousands of ultralight probes. Each one is no larger than a microchip. Each one weighs only a few grams. These tiny spacecraft are sometimes called star chips. They would carry only the essentials: a camera, a communication system, basic sensors, and a light sail. A thin, reflective membrane thinner than a human hair. The mission does not rely on carrying fuel. Instead, it relies on Earth itself. Gigantic ground-based lasers, possibly forming a phased array spanning kilometers, would fire an intense beam of light into space. This beam would strike the sail of each probe, pushing it forward with pure photon pressure. No combustion, no propellant, only light. And yet, this pressure, sustained and concentrated, could accelerate these tiny probes to around 20% of the speed of light. That is roughly 60,000 kilometers per second. At that speed, the distance to Proxima Centauri, 4.2 light-years, could be crossed in about 20 years of travel time. For comparison, The fastest spacecraft ever built by humanity would take tens of thousands of years to reach the same destination. Even at unimaginable speeds, the stars remain brutally far away. Interstellar space is vastly larger than human intuition understands. But Breakthrough Starshot is not just about acceleration. Before we continue, consider liking the video and subscribing so you don't miss what comes next in our exploration of distant worlds. The engineering challenges are extreme at every stage. The laser system alone would need to operate at unprecedented power levels, firing continuously with perfect precision to keep the sail stable during acceleration. Even the slightest deviation could destroy the probe or send it off course into interstellar darkness. Then there is the sail itself. It must be incredibly reflective to avoid vaporizing under the laser's energy. It must be perfectly stable under extreme acceleration. And it must remain intact despite being pushed by a force strong enough to accelerate it to relativistic speeds within minutes. But even if the launch succeeds, the hardest problems come later. Because the space between stars is not empty, it contains dust. Microscopic grains traveling at enormous relative velocities. At 20% the speed of light, even a particle smaller than a grain of sand can behave like a bullet carrying explosive energy. A single impact could damage or destroy a probe entirely. Then comes communication. At 4.2 light-years away, even a signal traveling at light speed would take over 4 years to reach Earth. And the probe itself would be extremely small and have limited power. Sending data back would require ultra-efficient transmission systems and possibly laser-based communication aimed precisely at Earth across interstellar distances. And there is one more fundamental limitation, one that cannot currently be solved with known physics and engineering. The probe cannot slow down. There is no onboard fuel, no braking system, no time to orbit. It would fly through the Proxima Centauri system at less than a quarter of the speed of light, crossing the entire planetary region in just minutes or hours. That means everything must be captured in a brief flyby. Images of planets, atmospheric readings, magnetic field data, and any possible signs of oceans, continents, or habitability. Then it would continue into interstellar space forever, a one-way snapshot of another star system. But even with all these limitations, the significance is enormous. For the first time in history, humanity is not just imagining interstellar travel, it is designing a method that, in principle, could work within a human lifetime. If successful, the first images ever received from Proxima Centauri b would not come from telescopes. They would come from something we built here on Earth, something small enough to fit in your hand, yet capable of crossing the distance between stars. And those first images would change everything. Because no matter what they show, a living world, a frozen wasteland, or something in between, humanity would finally be looking at another planetary system not through distant light, but from a messenger that was actually there. But before humanity can ever reach another world, we must first understand what is actually waiting there. Despite being the closest known, potentially habitable exoplanet beyond our solar system, humanity still cannot directly observe Proxima Centauri b. But we know its orbital period, its minimum mass, and the amount of stellar energy it receives. But the fundamental questions remain unresolved. Does it retain an atmosphere? Could it host clouds or oceans? Or is it a barren, radiation-exposed surface? Even the James Webb Space Telescope, the most powerful space observatory ever launched, faces significant limitations when studying Earth-sized planets around active red dwarf stars, such as Proxima Centauri. Most exoplanets, characterized in detail by the James Webb Telescope, are observed using the transit method. When a planet transits its host star directly from our perspective, the star's light briefly dips, a tiny eclipse. By measuring how much light is blocked, scientists can determine the planet's size relative to its star. The time between these dips reveals the planet's orbital period, essentially how long it takes to complete one full orbit. With that information, scientists can also estimate how far the planet is from its star, and, in turn, its potential surface temperature. In some cases, when starlight filters through the planet's atmosphere during transit, researchers can even detect traces of gases such as water vapor, carbon dioxide, or methane. This technique has been successfully demonstrated on worlds such as WASP-39b, where the James Webb Telescope has directly detected carbon dioxide, water vapor, and sulfur dioxide, providing one of the clearest atmospheric characterizations of an exoplanet to date. However, not all planets are equally accessible. Even TRAPPIST-1, a rocky planet in a nearby red dwarf system, discovered in the same way, remains challenging to characterize in detail. Its atmospheric properties are still uncertain due to the intrinsic faintness of the signal and the strong stellar activity of its host star. Proxima Centauri b presents an even more extreme case. It does not appear to transit its host star from our perspective, eliminating the primary method used for atmospheric characterization. So how do we even know Proxima Centauri b exists at all if we have never seen it? The answer reveals one of the most powerful techniques in modern astronomy. We did not discover it by the transit method or by taking a picture. We discovered it by watching its star. Proxima Centauri is not perfectly still. Even though it looks fixed in the sky, it is constantly being pulled back and forth by the gravity of orbiting planets. This creates a tiny motion, a stellar wobble. As the planet orbits, the star moves slightly toward Earth, then slightly away from it. When it moves toward us, its light shifts slightly toward blue. When it moves away, its light shifts slightly toward red. This is called the Doppler effect. By measuring these incredibly small shifts over time, astronomers noticed a repeating pattern. Every 11.2 days, something was consistently pulling the star in a rhythmic cycle. That repeating signal was the fingerprint of an unseen world. This technique is called the radial velocity method, and it is how Proxima b was discovered. But the transit method is one of the most powerful techniques for discovering and studying exoplanets. And here is the problem. Proxima Centauri b likely does not transit Proxima Centauri from our perspective. So one of humanity's most powerful techniques for studying alien atmospheres becomes extremely difficult here. No dimming, no atmospheric filtering, no direct planetary silhouette. The radial velocity method is what revealed its existence. But that method also has limits. It tells us the planet's minimum mass, its orbital period, and its distance from the star. But it cannot show its surface. It cannot reveal oceans or continents. It cannot tell us whether the planet is alive or dead. So humanity is left with an incomplete picture. A world we know is there, but one we still cannot truly see. And that is what makes Proxima Centauri b so powerful in modern astronomy. It is not just a discovery. It is a reminder of how far our vision still has to go. In the end, Proxima Centauri b remains a question humanity has yet to answer.
If you enjoyed this journey, consider liking the video and subscribing to more explorations into the cosmos. And let me know in the comments what you think we might find on this nearby world that remains far beyond humanity's reach.